The present invention relates to internal combustion engines, particularly four-stroke and reciprocating piston engines, primarily designed for propelling various transport vehicles such as cars, trucks, naval ships, etc., as well as for stationary facilities like power plants. The invention addresses the efficiency limitations of conventional crankshaft engines by proposing a new and innovative design, enabling the engine to achieve an extended power stroke compared to that of compression. This feature empowers the engine to attain high thermal efficiency, leading to a significant reduction in fuel consumption and, consequently, a decrease in CO2 and NOx emissions. Before we delve into specifics and explore the details of the invention, let's first provide an overview of a conventional crankshaft engine known in the prior art. The most widely used IC engines are four-stroke reciprocating engines, consisting of one or more cylinders. Within each cylinder, a piston performs reciprocating movements, which are reversibly transformed into continuous rotation of an output shaft through the conventional crank-Conrad mechanism, commonly implemented in the majority of reciprocating engines. The cylinder and the piston define a combustion chamber whose volume undergoes a cyclical variation, enabling the implementation of the four-stroke cycle, according to the operating principle widely known in the prior art. The PV diagram in the left side provides a visual representation of how pressure and volume change throughout the engine cycle. It offers a valuable tool for analyzing the thermodynamic behavior of the engine, as well as identify potential areas for improvement in terms of energy conversion and fuel efficiency. The useful mechanical work extracted from heat equals to the surface area of the blue region on the diagram. Subsequently, thermal efficiency is calculated as the ratio of the work performed to the heat input. Furthermore, as we can see on the diagram, since the expansion and compression ratios are equal, the pressure at the end of the power stroke remains higher than atmospheric pressure. This means that the expanding gases still retain residual energy, which cannot be efficiently converted into mechanical work as the piston inevitably ascends above the BDC. This residual energy will be released when the exhaust valve opens, being wasted in the case of naturally aspirated engine or recovered to improve power density in the case of turbocharged engine. The efficiency of engines relying on the crank-Conrad mechanism is thus inherently limited. To overcome this limitation, it would be pertinent to lower the pressure at the end of the power stroke as much as possible to extract maximum work from the combustion process. This can be accomplished through the ATKINSON cycle, characterized by an expansion ratio greater than that of compression. In practice, modern vehicles use the late intake valve closure technique to implement the ATKINSON cycle with a crankshaft engine without making significant changes to its structure. This technique involves keeping the intake valve open beyond the BDC to allow reverse flow of the air previously admitted through the intake manifold. The piston initiates effective compression only after the intake valve closure. Around 20 to 30% of the admitted air is expelled out through the still open intake valve. As a result, the effective compression ratio is reduced, while the expansion ratio remains unchanged. The engine thereby implements the ATKINSON cycle, which allows for the conversion of the most energy provided by the expanding gases during the power stroke into useful mechanical work compared to the OTTO cycle. As illustrated on the PV diagram, the pressure at the end of the power stroke decreases as the expansion stroke is extended compared to that of compression. The extension ratio REC, defined as the ratio of the expansion ratio to that of compression, represents a key feature for the energy conversion of the engine. A greater extension ratio leads to a lower pressure at the end of expansion, enabling for more energy to be extracted from the combustion process, and thus enhancing the overall engine's thermal efficiency. With an appropriate extension ratio, the conventional engine employing the LIVC technique can achieve a thermal efficiency of up to 18% compared with the OTTO cycle engine. Although the LIVC technique offers significant efficiency enhancement, it comes at the expense of power density and peak torque. In fact, the shorter compression stroke means that the engine takes in less available air-fuel mixture for combustion than an equivalent OTTO cycle engine, resulting in a lower charge air density and consequently, a potential reduction in overall performance and power output. In hybrid modern vehicles powered by an Atkinson cycle engine, the lack of power is compensated for by an electric motor during times when additional power is required. The present invention, named Planetary Engine, is a cutting-edge innovation in design that not only achieves enhanced efficiency through the implementation of the Atkinson cycle, but also delivers high power output, setting a new era in powertrain technology by seamlessly combining high performance, sustainability, and low environmental impact. The Planetary Engine consists of three main systems. The cylinder block positioned at the center and flanked on either side by the active and passive units. The cylinders block comprises one or more coplanar cylinders, radially arranged around the output shaft's axis. Each cylinder houses a piston, rigidly connected to its rod by means of two pins. The piston rod has at its end a bearing with an open half-cylindrical shape, deprived of a rod cap. The piston and its rod assembly are configured to move longitudinally along the axis of the corresponding cylinder. Since the piston rod is not linked to any crank pins due to the open shape of its bearing, the piston can slide freely inside its corresponding cylinder. The axes of the cylinders are called mains axes of the engine, X and Y. The second main system is the active unit, whose primary role is to convert the force exerted by the pistons during the power stroke into rotary torque at the output shaft, driving the passive unit and ensuring the compression stroke. The active unit consists of a set of components arranged such as to form a planetary gear train. The output shaft is rigidly connected on its end to the sun gear. The planet gear includes a primary gear wheel capable of meshing with the ring gear, while being maintained in its orbit by the planet carrier. The output shaft is rotationally driven by a secondary gear wheel integrated into the planet gear engaging with the sun gear. The transmission ratio of this gear train does not impact the engine power output. However, its value is defined so that, similarly to the crankshaft engine, the output shaft completes 2 revolutions during the 4-stroke cycle. The active connecting rod, fitted with a number of crank pins equal to that of the main axis, is rigidly mounted on the planet gear and arranged in such a way that, when the planet gear rotates around the z-axis, each crank pin performs a reciprocating movement along its corresponding main axis. The active unit, which is designed to be driven by the pistons, therefore, achieves a reversible transformation from reciprocating movement of the crank pins into continuous rotation of the output shaft. The third main system is the passive unit, whose primary role is to ensure the completion of the remaining intake and exhaust strokes required to achieve the 4-stroke cycle. The passive unit is driven in rotation by the active unit through the axis of their planet gears, called drive arms. In fact, each planet gear of the active and passive units is connected at the second end of its axis by a pivot linkage to the planet carrier of the opposite unit. In other words, each planet gear is guided in rotation around its axis by both planet carriers. The passive unit consists of a set of components arranged such as to form a planetary gear train. Likewise, akin to the active unit, the passive connecting rod, fitted with crank pins, is arranged in such a way that when the planet gear rotates around the z-axis, each crank pin performs a reciprocating movement along its corresponding main axis. The passive unit, therefore, achieves a reversible transformation from rotational movement of its planet carrier into reciprocating movement of its crank pins. To understand how the 4-stroke cycle is implemented in the planetary engine, it's crucial to emphasize the interaction principle between the piston rods, which are deprived of a rod cap, and the crank pins of the active and passive connecting rods. each piston alternatively interacts between the active and passive crank pins that reciprocate along its corresponding axis in a spontaneous manner. Due to the open shape of its bearing, the piston rod is able to interact with the crank pins only through simple thrust. This implies that the crank pins cannot pull the piston in any way. The piston rod switches from the passive to the active crank pin to initiate the compression stroke. The piston rod switches from the active to the passive crank pin to initiate the exhaust stroke. It's worth noting that within this interaction mode, only the compression, expansion, and exhaust strokes can be achieved, during which the piston rod and the crank pins repel each other. As previously mentioned, the implementation of the four-stroke cycle is distributed between the two units of the planetary engine as follows. The active unit achieves the compression and the expansion strokes, while the passive unit ensures the remaining intake and exhaust strokes. As we can see, during the compression stroke, the active crank pin AX pushes the piston towards the TDC. Hence, the rod cap is not necessary. During the expansion stroke, the piston rod, in turn, pushes back the active crank pin AX. Hence, the rod cap is not necessary. Likewise, during the exhaust stroke, the passive crank pin PX pushes the piston towards the TDC. Hence, the rod cap is not necessary. The intake stroke is the only phase during which it is necessary to pull the piston to draw air into the combustion chamber. To achieve this, a hooking mechanism is required to establish a temporary linkage between the piston rod and the passive connecting rod, enabling the latter to pull the piston during the intake stroke, and releasing it at the beginning of the compression stroke. The hooking mechanism is designed as follows. The passive conrod comprises at its extremity a groove opened on both sides, while the piston rod is fitted with a finger capable of sliding within this groove during the intake stroke. The groove is designed so that the finger enters through the inlet side at the beginning of the intake stroke, allowing the passive connecting rod to hook onto the piston rod and pull it to draw in air into the combustion chamber. The finger exits from the groove through the outlet side, allowing the passive connecting rod to release the piston at the beginning of the compression stroke. The angular interval of the groove is configured to restrict the linkage established by the hooking mechanism only during the intake phase. The planetary engine enables, therefore, the implementation of the four-stroke cycle through a sophisticated interaction mechanism between the pistons and the active and passive units, showcasing a novel approach to internal combustion engines. We will discover that this innovative design opens up potential area for enhancing efficiency and overall performance. As described earlier, we can observe that the piston rod is constantly engaged with either the active or passive crank pins even without a rod cap. The active crank pin AY engages with the piston rod at what is called the first switching point FSP, marking the start of the compression stroke. The passive crank pin PY engages with the piston rod at what is called the second switching point SSP, marking the end of the power stroke. In this specific embodiment of the planetary engine, the FSP and the SSP coincide with the point O, resulting in equal compression and expansion stroke. To highlight the advantages of the planetary engine in terms of efficiency and output power, it is pertinent to conduct a comparative analysis with a conventional crankshaft engine of equivalent displacement and stroke length. At the TDC, in both engines, the lever arm is zero, meaning that the gas pressure force has no effect on either the crankshaft or the active con rod, resulting in zero output torque. In an intermediate position, in the crankshaft engine, the gas pressure force acting on the piston generates a parasitic side force pushing the piston against the cylinder. This side force significantly increases the friction between the piston rings and the cylinder liner, which is responsible for the major part of energy loss, and that contributes to about 40% of the total frictional losses in a crankshaft engine. On the planetary engine, since the crankpin path aligns with the cylinder axis, the pressure force doesn't generate any side force pushing the piston against the cylinder wall, leading to a significant reduction of frictional energy loss, which makes the engine more efficient and more resistant against wear. As explained earlier, the pressure force at the end of power stroke remains higher than atmospheric pressure. In the crankshaft engine, at the bottom dead center, the lever arm is zero, meaning that the pressure force has no effect on the crankshaft, resulting in zero output torque. However, on the planetary engine, at the second switching point SSP, the lever arm reaches its maximum value. This key feature can be leveraged to directly convert the remaining residual energy at the end of power stroke into useful mechanical work. To achieve this, simply shift the SSP beyond point O to allow the piston to further drive the active conrod, thereby achieving an extended power stroke, leading to an efficient conversion of gas pressure force into output torque. The second embodiment of the planetary engine is a refined version of the initial design, involving slight adjustments to specific components, while maintaining the fundamental structure and overall operating principle. In this variation, the two planet carriers, which were initially configured so that the axes of the planet gears are symmetrical with respect to the z-axis, are replaced by asymmetrical planet carriers with an angular offset 2 beta. This configuration allows for the specific arrangement of the planet gears around the z-axis, as illustrated. As we can observe, the interaction of the piston rods with the active and passive con rods follows the same operating principle described earlier, though with a change in the position of the first and the second switching points along the main axis of the engine. The angular interval of the hooking mechanism is accordingly reduced by the angle beta, allowing the passive conrod to release the piston at the first switching point to initiate the compression stroke. We can clearly notice that the intake and exhaust strokes traveled by the pistons have different length. Consequently, the valve train system is readjusted to ensure a perfect synchronization of valve timing with the implementation of the 4 strokes. In contrast with the first, in the second embodiment of the planetary engine, the FSP and SSP are symmetrically located on either side of the point O, and the distance between them depends on the offset angle of the planet carriers. As a result, the piston travels an extended power stroke compared to that of compression, as it continues to push the active crank pin beyond point O. The engine thereby implements the ATKINSON cycle, allowing for more useful mechanical work to be extracted from the combustion process compared to the OTTO cycle. It's important to emphasize that in the vicinity of point O, the lever arm reaches its maximum values. This signifies that the piston's action on the active crankpin in this advantageous region generates the highest output torque, resulting in an efficient conversion of the residual energy into mechanical work. To evaluate the efficiency and output power of the planetary engine according to its second embodiment, Let's conduct a comparative analysis with the Atkinson cycle engine employing the late intake valve closure technique. The extension of the power stroke is accompanied by a shortening of the compression stroke. Precisely, the compression volume is reduced by the same amount added to that of expansion. In the case of the crankshaft engine employing the LIVC technique, the Atkinson cycle can be achieved solely by shortening the compression stroke. As previously explained, the extension ratio REC, defined as the ratio of the expansion ratio to that of compression, serves as an indicator of the Atkinson cycle efficiency. For example, with an extension ratio equal to 1.5, in the crankshaft engine with LIVC technique, the compression ratio is reduced by 33%, whereas in the planetary engine, the compression ratio is reduced by only 20%. In other words, the intake charge air compressed by the planetary engine is 20% greater than that compressed by the crankshaft engine with LIVC technique, which translates to 20% more power density in favor of the planetary engine. Therefore, given the same power stroke extension ratio, in other words, the equivalent energy conversion rate, the planetary engine still outperforms the crankshaft engine with LIVC technique in terms of power density. Although the second embodiment of the planetary engine provides a significant enhancement in efficiency compared to the first embodiment, this improvement comes at the cost of lower power density and peak output torque due to the shortening of the compression stroke. Ideally, enable the pistons to travel an extended power stroke while maintaining the compression ratio unchanged. The third embodiment of the planetary engine is a refined version of the second, enabling it to achieve an extended expansion without having to shorten the compression stroke. The structure of the active and passive units remains identical to the previous one with only slight adjustments made to the piston rods. In this variation, unlike the previous ones, the piston rod features two distinct bearings rather than a single common bearing. The first is intended to interact with the active crank pin, while the second is dedicated to the passive crank pin. The distance d between each bearing depends on the offset angle of the planet carriers. As the result of this modification, the passive conrod releases a given piston rod before engaging with the opposite one. In other words, the switching of the passive conrod from one piston to its opposite doesn't occur at the same time. The angular interval of the hooking mechanism is reduced by the same angle as the angular offset of the planet carriers. The four-stroke cycle is implemented according to the same operating principle previously described, though with a change in the position of the FSP and SSP along the mains axis of the engine. Unlike in the previous embodiments, the piston doesn't reach the TDC at the end of the exhaust stroke, leaving a residual quantity of burnt gases inside the combustion chamber. To tackle this issue, the exhaust valve is held open for a certain duration during the piston's descent. Concurrently, the intake phase is carried out with a pressure slightly higher than atmospheric pressure thanks to a supercharger, leading to the expulsion of the remaining burnt gases from the combustion chamber. The exhaust valve closes while the piston continues its descent to complete the intake stroke. The intake valve is then closed to initiate the effective compression. In this embodiment of the planetary engine, the FSP coincides with the point O, and the SSP is located beyond point O. The distance between the two switching points depends on the offset angle of the planet carriers. Consequently, the piston travels an extended power stroke as it continues to push the active crank pin beyond point O. This enables the engine to implement the Atkinson cycle and efficiently extract the maximum energy from the combustion process. To assess the efficiency and power density of the planetary engine in its third embodiment, Let's again conduct a comparative analysis with the crankshaft engine employing the late intake valve closure technique. As intended, we can clearly observe that the expansion stroke is extended without the need to reduce the compression stroke. This means that the engine compresses as much charged air as the Otto cycle engine, thereby avoiding any decrease in output power. To achieve an extension ratio REC of 1.5, the crankshaft engine employing the LIVC technique should expel 1/3 of the intake air from the combustion chamber, meaning that the charge air available for compression is 2/3 of that compressed by planetary engine according to the third embodiment. In other words, a 4-cylinder planetary engine delivers as much power density as a 6-cylinder crankshaft engine employing LIVC technique. This makes the planetary engine an economically viable and efficient alternative to traditional crankshaft engines, providing a compelling powertrain solution for applications where cost-effectiveness is a critical factor. The fourth embodiment of the engine aims to resolve the issue encountered in the third variation, where the piston doesn't reach the TDC at the end of the exhaust stroke. The goal is to avoid the need of a supercharger to ensure the intake stroke, making, therefore, the engine naturally aspirated. For this purpose, the active unit is kept unchanged, while the passive unit is fitted with a longer connecting rod than in previous embodiment. The other components are adjusted in consequence to ensure that the engine operates according to the same working principle as described earlier. These adjustments include modifications to the two planet carriers and increases in the diameters of the planet and ring gear of the passive unit. Similar to the third embodiment, the piston rods feature two distinct bearings. However, in this instance, the distance between these bearings is contingent upon both the angular offset of the planet carriers and the length of the passive connecting rod. The 4-stroke cycle is implemented according to the same operating principle previously described, though with a change in the position of the FSP and SSP along the mains axis of the engine. As intended, we can clearly observe that the piston reaches the TDC at the end of the exhaust stroke. All burnt gases are expelled from the combustion chamber, and the intake stroke can be carried out without the need for a supercharger. The planetary engine in its fourth embodiment presents all the advantages previously highlighted in the third variation, such as improving efficiency without compromising power density, as well as eliminating the need for the supercharger which is typically required for the intake stroke, and thereby avoiding the associated extra costs. Thanks to its restrictive architecture, the planetary engine can be customized by simply adjusting the angular offset of the planet carriers and the length of the passive conrod. The optimal choice of these parameters enables a significant enhancement in the overall performance of the engine. The planetary engine can be implemented in several configurations. The number of cylinders and their arrangement around the output shaft can be customized to meet the needs in terms of performance and space requirements. For example, the common V-engine configuration widely used as powertrain in the automotive sector can be obtained by setting two pistons radially arranged in two parallel planes, as illustrated. The flat or boxer engine, in turn, features 4 or more opposed pistons in the same plane. In this configuration, both the active and passive connecting rods are fitted with only one crank pin, moving along the axis of the two opposed cylinders. These two configurations are well suitable for use in vehicles' powertrain, while other setups with more cylinders can easily be designed for applications such as power generation or naval ships propulsion, in which the space requirement is not the primary concern. The Planetary Engine stands as a pioneering solution by seamlessly integrating the Atkinson cycle without compromising on compression ratio. This groundbreaking innovation not only enhances efficiency by reducing frictional losses and maximizing energy extraction from combustion process, but also delivers high power density without requiring for a turbocharger or electric motor. In an era where environmental concerns take center stage, the Planetary Engine's design actively addresses emissions and ecological impact, emphasizing a profound commitment to eco-friendliness and contributing significantly to a greener and more sustainable future.